This question was asked in CSIR June 2019 exam. The question reads like this: the major products A and B in the following reactions are, and this is the reactant molecule. Under this set of conditions, it gives product A, and under this set of conditions, which gives product B. In both the cases, the first set of conditions will generate the enolate, and next step in both the cases is adding enolate to a aldehyde and getting the product. And what is very important is what kind of a enolate we will generate when you use this set of conditions, and what kind of enolate is generated when you use this kind of a reagents. And look at the products. In the products, option 1, in both the cases, the product formed is syn product. The syn product means both the substituents on the newly created newly created chiral centers are cis to each other. These are two substituents, and they are cis to each other. And in the option B, they are trans to each other. So this is called anti-product. And in option C, this is a syn product, and this is anti-product. In option 4, this is anti-product, and this is syn product. What we should know here is what kind of a enolate is generated when you use these conditions, and what kind of a enolate is used when you use this set of conditions. So what you should notice here is, in this case, is what kind of a substituents you are having on the boron reagent. You have on the boron reagent, this boron reagent is dicyclohexyl boron chloride. This cyclohexyl groups are bulky. Now you have a bulky boron reagent is used here for getting the product B to generate the enolate from this starting material. And we'll see what kind of a enolates are generated from this starting ketone, and for the product towards A using LDA conditions. This is the product towards conditions towards A. The conditions towards A are LDA conditions. Under LDA conditions, lithium diisopropyl amide conditions, the enolate formed is cis enolate. So this enolate is a cis enolate that you could decide based on assigning the priorities to the substituents present on these two sp2. This takes priority 1, and this also takes priority 1, as same priorities are on same side. So we will take it as a cis product. And the conditions which are leading to product B are, these are the conditions for conditions which lead to product B are the bulky boron reagents, dicyclohexyl boron chloride and triethylamine. That conditions would give you a trans enolate is formed. You could see the trans enolate, and then you add this cis enolate to a propanol, and this step is the transition state for adding enolate to the given aldehyde. In this case, a cis, you will start when you start with a cis enolate. This is the cis enolate, and you could easily see that this oxygen and this methyl are on same side. This oxygen and this methyl are on same side, and this phenyl and this hydrogen are on same side. So we have retained the cis enolate in the cyclic transition state, and this part is the aldehydic part. In this aldehydic part, what is very important is you must be knowing the two substituents which are present on the carbonyl carbon of the aldehyde. The carbonyl carbon of the aldehyde will be having one hydrogen substituent, and the other one is ethyl substituent, and the smallest one will take a axial position, and the other one will take the approximately equatorial position. So we would always write the smaller substituents of the aldehyde on the axial position. The other one will be to equatorial position. Now in this case, what you should observe is these two hydrogens are on same side. These two hydrogens are on same side. So it would become syn product. Or you can also take this CH3 and H are on same side. So a syn product is formed. And when you add the enolate, what kind of enolate? Cis enolate to an aldehyde, you will get syn product. In this case, the bulky boron reagent, when bulky boron reagent is used to generate enolate, a trans enolate is formed. So this trans geometry is maintained in the cyclic 6-membered transition state also. Look at this trans geometry is maintained, and same aldehyde is written here. In the aldehyde, what is very important is the hydrogen which is smallest will take the axial, the other substituent would take the equatorial position. And what you should observe here is, then you could now to see the mechanism, this bond electrons would come on to the, this bond makes a double bond, then this pi electrons through this carbon will add to this carbonyl carbon, and this O will become O minus, that will become protonated to give OH. Then what is observed is these two hydrogens are trans to each other, or they are anti to each other. So you will get anti product. So CH3 and OH are anti. So we will get anti product. From trans enolate, we will get anti product. From cis enolate, we will get syn product. Now, so these are the conditions which are used to produce, cis enolate. So cis enolate would add to the aldehyde, gives syn product. Now you could see this syn product here. See, methyl and OH are on same side, and you could see the hydrogens which is below the plane here. The hydrogen here also is below the product. With this set of conditions, you would produce trans enolate. Then trans enolate would add to the aldehyde, give anti product. So the answer for this question is option 3.